All right, so today we're going to do something pretty cool. We're going to build a digital brain right from the ground up. The idea here is to really get a gut level feel for the fundamental concepts that power artificial intelligence. So let's jump right in. I mean, think about it. AI is everywhere, right? We've got self-driving cars navigating city streets, our phones instantly recognizing faces and photos. But how does it actually work? How on earth does a machine learn to do things that feel so, well, so human? That's the big question we're going to unpack today. Now, you might think that the secret is just some programmer writing millions and millions of if-then rules. If you see this pixel pattern, then it's a cat. But for really complex problems, that's just impossible. The real game changer, the big breakthrough, was moving away from those rigid, hard-coded rules to systems that learn patterns on their own just by looking at tons of data. So let's kick things off by looking at exactly why those old rule-based approaches just can't keep up. To understand something as messy as the real world, a machine would need a nearly infinite number of rules to cover every single possibility. And this slide really lays it out perfectly. On the left, you have the old way, hard-coded rules. The problem is, they're brittle, they're inflexible. The second they encounter a situation the programmer didn't think of, they break. But on the right, you have the new way, learning from data. These systems can adapt, they improve over time, they can handle the messy, unpredictable nature of the real world, and that's what makes them so incredibly powerful. So, if it's not a giant list of rules, then what is it? Well, the answer is a structure that's actually inspired by our very own brains. Let's crack open this digital brain and take a look at its core component, the neural network. At its heart, a neural network is just a system of interconnected neurons that are organized in layers. You've got an input layer that takes in information, an output layer that spits out the decision, and in between, one or more hidden layers where all the complex thinking happens. But here's the real magic. It learns by adjusting the strength of the connections, the weights, between all of those neurons. But before we can really wrap our heads around the whole network, we need to understand its most basic building block. So let's zoom way in and look at just a single one of these brain cells to see how the idea of a neuron that can learn actually came about. The earliest model was called the McCulloch-Pitts Neuron. The easiest way to think of it is as a simple logic gate. It takes in a few signals, and if the total signal crosses some fixed threshold, it fires. Simple enough. It's great for basic logic, but, and this is a big but, it has a fatal flaw. It can't learn. Its rules are locked in. It can never get better or change based on experience. And this really shows you why. The decision is totally binary. It's either on, a 1, or it's off, a 0. This is what's known as thresholding logic. It's basically a simple light switch. There's no dimmer, no in-between, and the switch itself can't learn to become more or less sensitive on its own. Then came the big leap forward, the Perceptron. This brilliant little upgrade solved the single biggest problem of its predecessor, because this neuron can actually learn. When it makes a mistake, say it calls a spam email not spam, it goes back and adjusts its internal weights to try and do better next time. In short, this neuron learns from its errors. Okay, so now we have a neuron that can learn. Awesome. Let's zoom back out to the whole network. So how does this whole collection of neurons actually get smarter? Well, it all comes down to a really simple but incredibly powerful cycle. It makes a guess, it checks how well it did, and then it corrects itself. Over and over again. This brings up a really important question, right? For a network to correct itself, it has to have some way to measure just how wrong its guess was. I mean, how does it know if it was just a little bit off or totally, completely wrong? The answer is something called a cost function. And honestly, the best way to think about it is as the network's teacher. It's a piece of math that gives the network a score on its performance by calculating the difference between its prediction and the actual right answer. A high score, or a high cost, means you made a big mistake. A low cost means you're getting really close. And this brings us to the engine of learning itself, a process called gradient descent. So let's walk through this loop. First, the network makes a guess. Second, the cost function tells it how wrong it was. Third, and this is the genius part, the process figures out which of its connections, which weights, were most responsible for that error. And finally, it adjusts those specific weights just a tiny bit to reduce the error. It's like walking downhill in the fog, step by step, always moving in the direction that leads to the lowest possible error. Now, there's one more absolutely crucial ingredient we need to talk about, the activation function. This is what makes the final decision on whether a neuron should fire or not. But instead of just a simple on-off switch, modern activation functions allow for more nuanced outputs, kind of like a probability. And this little detail is what gives the whole network its power. Without it, the entire system would just be a fancy but simple linear equation. This is what lets it learn all the complex, curvy, nonlinear patterns that we see in the real world. So we've got our network, and we've got a way for it to learn. But, just like in a classroom, there are different teaching styles. So let's take a quick look at the different ways a network can actually be trained. There are 4 main styles. Supervised learning is like studying with flashcards. You give it data that's already labeled, like pictures of cats that are labeled cat. Unsupervised learning is the opposite. You give it a bunch of unlabeled data and it has to find the hidden patterns on its own. Semi-supervised is a mix of the two. Really useful when labeling all your data is just too expensive. And finally, you've got reinforcement learning, which is all about trial and error, using rewards and penalties. This is how you teach an AI to play a game or a robot to walk. Okay, let's talk about the practical side of training this thing. Because just like with us humans, for a neural network to really, truly learn something, it needs practice. And I mean a lot of practice. Repetition is absolutely everything. And there are 2 terms you'll hear thrown around all the time: epoch and iteration. An epoch is one full pass of the entire training dataset through the network. Think of it like reading a textbook from cover to cover one time. An iteration, on the other hand, is just a single update of the network's weights. It's like doing one practice problem from the textbook. So you have many, many iterations inside of a single epoch. So why do we bother stacking all those hidden layers on top of each other? What's the point? Well, this is the entire essence of deep learning. The first layers learn to see really basic patterns, like simple edges and colors. The next layers combine those to see more complex shapes. Deeper layers then combine those shapes to recognize things like faces, or cars, or animals. The network literally builds a complex understanding of the world from simple little pieces, layer by layer. So there you have it. We've gone from a simple on-off switch to a neuron that learns from mistakes, and then to a full network that gets smarter with every single guess. We've basically built the blueprint for a simple digital brain. So the only question left is, what happens when we scale this up? What happens when we connect not just a handful of these, but millions or even billions of them together? That is where today's AI revolution truly begins.